Okay, so next we'll prove the theorem. Let the set X together with some topology tau be a topological space and let the collection script B, consisting of sets B sub I, for I in some indexing set I, be a basis for the topology tau. Then a subset of the space is open if and only if for every point in that set there exists a basis element containing that point, and that basis element is itself a subset of the given set U. So proof. Suppose that a subset of the space X is open, then this set is a union over some index J of elements B sub J, where the index J is a subset of the indexing set I in the basis. That is, the set U is a union of some elements in the basis. There are two cases. That we will consider. Case 1, the indexing set J is not the empty set. So let a point X be in the set U, which again is a union over index J of elements B sub J. Then the point X is in the set B sub J for at least one index J in the indexing set J. Further, the set B sub J is a subset of the union of all such subsets for every choice of index J. And so the point X is in this set B sub J, which is a subset of the set U. That is, for every point in the open set U, there exists a basis element such that the point X is in that basis element, and that basis element is a subset of the open set U. So case 2, the indexing set J is the empty set. Then the set U is the empty union, and so is the empty set. So the result follows vacuously. So conversely, suppose that a subset U of the space X satisfies the condition that for every point in the set U there exists an element B sub I in the basis such that that point is in this basis element, and the basis element is itself a subset of the set U. So let X be some specified point in the set U. Then there exists a basis element, B sub I, which contains that point, and which is a subset of the set U. Now, as the set B sub I is a subset of the set U, which is itself a subset of the space X, we have that the complement of the set U is a subset of the complement of the basis element B sub I, where that complement is closed, as it is the complement of an open set. And so we have a closed set containing the complement of the set U. And so the closure of the complement of the set U is a subset of the complement of the basis element B sub I. Now, as the point X is in the basis element B sub I, that point is not in the complement of the basis element B sub I. And so the point X is not in the closure of the complement of the set U, which is the same as the complement of the interior of the set U. And hence, the point X is in the interior. And so we have that given a point in the set U, that point is in the interior of the set U. And so the set U is a subset of its interior. And thus, the set U is open. All right? Now, in any topology, the entire set X is open. And so we have, by the previous theorem, that for every point X in the space X, there exists an element B sub I in the set script B, where script B is a basis for the topology, such that that point is in the basis element B sub I, which is a subset of the space X. That is, for every point in the space X, there exists at least one basis element containing it. So next we'll prove a corollary of the theorem. Let X, together with some topology tau, be a topological space. And let the collection script B, consisting of elements B sub I for I in some indexing set I, be a basis for the topology tau. Then the space X is the union of the basis elements. So proof. Let the point X be in the space X. Then there exists an element B sub I in the basis such that X is in that basis element, which is a subset of the space X. Now, as each basis element is a subset of the union of basis elements, and this is for any index I, we have that the point X is in this union of basis elements. Indexing set is I. That is, given a point in the space, that point is in the union of basis elements. And so we have the set the entire set X is a subset of the union of basis elements. Now the reverse inclusion is obvious. Since B sub I is a subset of the space X for every index value I. And so we have set inclusion in both directions so that the space X is the union of basis elements. So now we'll give a new definition. Let the collection script A, consisting of sets A sub I for I in some indexing set I, be a collection of subsets of a space X the collection script A is said to cover the space X, or to be a covering of the space X if and only if that space, the entire space, is the union of the elements in the collection. If the elements in the collection are open sets, then it is called an open covering of the space X. So notice that a basis for a space X is an open covering of the space, and this is one of the important properties of a basis So as a corollary, we will show one of the other important properties of a basis. So let a set X together with some topology tau be a topological space. And let the collection script B, consisting of sets B sub I for I in some indexing set I, be a basis for the topology tau if a point is in the intersection of two basis elements then there exists a third basis element, which we'll call B sub 3, such that the point X is in this third basis element, which is a subset of the intersection of the two basis elements B sub 1 and B sub 2. So proof. Each of the basis elements is open, and so the intersection of two basis elements is open, as it is a finite intersection of open sets and so by the previous theorem, we have that for every point x in the intersection of B1 with B2, which is an open set, there exists at least one basis element which we'll call B sub 3, such that the point x is in this basis element, which is a subset of the given open set, which in this case is the intersection of two basis elements. Okay, so next we will give the solution to the last exercise from the previous theorem, or rather from the previous lecture. Let the collection script B be the set of all subsets U of X such that the point P is in the set U, and let U sub 1 and U sub 2 be two such sets. Suppose that a point X is in the set U sub 1 and that same point is in the set U sub 2. Then that point is in the intersection of U sub 1 and U sub 2. So we consider two cases. Case 1, the point X is the specified point P. Then the singleton containing that point P is a subset, or is contained, or is an element in the collection script B, such that the point P is in the singleton containing it, which is a subset of the intersection of U sub 1 with U sub 2, since the point P is in the set U sub 1 and the point P is in the set U sub 2. So case 2, the point X is distinct from the point P. Then the two-point set containing the point X and the point P is a set in the collection script B, such that the point X is in this two-point set, which is a subset of U sub 1 intersected with U sub 2, since both the point X and P are in the set U sub 1, and both points X and P are in the set U sub 2. So if a point is in the intersection of U sub 1 and U sub 2, where U sub 1 and U sub 2 are elements in the collection script B, then there exists at least one element in the collection script B, which we'll call U sub 3, such that the point X is in this element, which is a subset of the intersection of U sub 1 with U sub 2. So notice that in this example, we are not saying that the collection script B is a basis, because we did not define a topology, but it should be clear what topology we have in mind. We simply add the set which contains the empty set, and we have the particular point topology. So the question is, what is the condition on a collection of sets that makes it a basis for a given topology? And we'll answer that in the next theorem.